Friday morning. Paolo Cascini from Imperial College London, and he will speak about on the minimal model program for foliations.
Okay. So, very much benefited from mathematics, like many of us, I suppose, mathematics of professorship. So, thank you very much for organizing it, for giving me this opportunity. So, lately, I even had the honor to work with professorship, so I'll talk a little bit about some of the topics. So, in particular, I'll talk a bit about foliations. So, I'm sorry if you heard this a few times. I will be very brief from introduction, but I need to introduce the notation. So, what is a foliation? So let's consider a normal, most of the time projective variety, and most of the time over the complex numbers, actually all the time over the complex numbers, and the dimension n. So a foliation on X so the foliation f on X is the data of, sorry, I should say rank of foliation of for X. It's a data of a subsheaf. It's a coherent subsheaf. Rank R. Coherent subsheaf. Which we usually denote by TF, just to differentiate from the letter F, of Tx, of the tangent sheaf of X. We satisfy the two following properties. So first of all, if you define the quotient of Tx over Tf, this is quotient 3, which is always possible to obtain by just taking the substitution of whichever subsheaf you consider. And the most important property is that Tf is closed under the bracket. So, and this is crucial to the rules. So I'll talk a little bit about that because of a minute. But let me define first. So X is not smooth, and also F is not smooth. So what does it mean? So let me define. So once we have this subsheaf, we clearly have a natural map from the double dual of the arc wedge of omega 1 of X tensor, and I'm going to define what this is. Yes. Minus TF. So what is minus TF? This is any device. It's going to be the canonical device. So it's any device on X, such that it's a bit like the canonical. It's such a canonical device. The sheaf associated is just the determinant of the dual of the tangent sheaf of the foliation. Okay, so we have a natural map from this sheaf to X. And by definition, the singular locus of F is the center point. Sorry, it's the co-support, maybe let's just say. It's the co-support of this map. So we define it's the co-support of F. So if X is smooth, this coincides with the locus where this sheaf here is not, the normal sheaf is not a subbundle of, the dual is not a subbundle of over 1X. In general, this happened to be a better definition of the singular locus, but it's not going to be relevant for what we're going to say. What is going to be probably more relevant is Frobenius theorem, which is very classic, but since I needed to define leaves, I'm going to mention it. So if X, for any X, which is not contained in the singular locus of X, nor in the singular locus of F, we know that the foliation is induced by a holomorphic morphism. So there exists an open subset U of X, which is analytic open. And also there exists an holomorphic map, let's call it sigma, into C n minus R, where R is the rank of the foliation, such that basically what we have is that one way to see it is that the normal sheaf of F restricted to U is nothing but the pullback of the tangent bundle of this variety.
Sigma.
Yes.
Sigma.
Sigma. Thank you. Okay, so this is very much an analytical tensor set. So it's most of the time it's impossible to find an algebraic open subset that is satisfy this property. But this is exactly what characterizes algebraic linear foliation, which we're going to see later on. So what is the picture? The picture is just that we have on morphism from an open subset of X into some copy of CNMR, the previous space. So the fibers of this morphism, which have dimension R, are what they call the leaves. So more precisely, a leaves is a union of what they are locally fibers of this morphism. And it behaves well, of course. If you match together two different views, you get exactly the same definition. Okay, so this would play a role, a role in the study of the foliation. So let me say, what are we trying to do? So this is called the canonical device of the foliation. And we'd like to understand how the birational geometry of foliation is related to the classic minimum of the problem. And before doing that, we need to understand if I have a birational morphism, can I use a foliation for one variety to another? And the answer is yes. So more in general, suppose that phi is any birational map. And suppose that F is a foliation X. So it's very easy to show that there exists a unique foliation of Y, which is naturally induced by phi. So there exists a unique Fy foliation induced on Y, which has the property, of course, that on the open set where X and Y are isomorphic, they coincide. Okay, so it really makes sense if we have varieties up to birational map. It really makes sense to understand how does this device behave by changing moment. So, for instance, can we make the F and F? And also another question that we might want to ask is why do we care? And I'll try to answer this question. I mean, I will try to do some applications. Actually, the whole point is to do some applications. But before doing that, I mean, we know from the name of the program that working with smooth object is not enough. Of course, foliation almost never smooth. But also, we know that working with just one object is not enough, meaning that usually with varieties we work with pairs. And here we need to do exactly the same thing. We need to work with pairs. So we need to allow singularity in some sense. So what is a pair? So for me, a pair would be, I mean, the standard notation is that we consider a pair F delta, where of course this is a foliation, and this is a Q divisor. For today, this Q divisor will be always effective. Of course, you can, I mean, generalize into different contexts. But the most important thing is that, as usual, we want the F delta to be exactly like in the world of log pairs. Okay, so by doing this, we can define singularities. I mean, by considering this object, we can define singularities. But before I do that, let me define what is an invariant divisor. So let's suppose that we have a divisor in your X, and there will be a reason why which is a divisor, or another surface in this divisor. So this is called invariant. Okay, this is not quite the correct definition, but for upper surfaces it works quite well. So then, or maybe I should say F invariant, sorry. If it's a union of leaves. I mean, of course, you can only do this in the smooth locus, but since it's an upper surface, it makes sense. Because dimension to both the foliation and the variety X are smooth. So it makes sense that to say that it's it is linear. Okay, again, it's a little bit of a approximation of the correct definition, but for today it should be good enough. And the notation that I'm going to use, I will be clear in one moment, is that if this is the case, then I will say that epsilon is equal to 0. Okay, just a notation. If not, we will say that if E is not invariant, and I will justify why this number makes sense. Then we just write epsilon E to be equal to 1. So maybe let me just do it now. Why do we care about this number, and why the singularity depends on this number? So the main reason is a junction. Actually, probably the only reason is a junction. So let's suppose we live in a nice world. Of course, you can do it in a much more general context. But let's suppose that the S and X are smooth. So it's a smooth variety with a smooth upper surface. So as usual, we would like to understand what happens when I restrict to S. As usual, when I do a junction. So the idea is that, so I want to understand what happens if I restrict this thing to S. Well, if you think about the usual varieties, we need to add S, right? And we should have something like K of something plus something like that. So let me say the statement. The correct statement is that here is not 1, but it's epsilon S. So it really makes a difference to know whether this upper surface is invariant or not, if invariant or not. And what is the so delta is like different, and it's always a type. So the reason why it's non-zero, although I'm taking everything smooth here, is because of course there could be similarity in definition, which are almost always there. Assuming the type is smooth is not a good idea. So there will always be some kind of error. And what I'm missing here, I need to say what is the case that we're considering. So I don't want to spend too much time. I'm just trying to motivate this number. The definition I'm going to give you in 1 minute. But what is missing here is F of S. So where F of S, it's an induced solution. It's an induced solution. You can figure out what it means. So the only thing that you need to be careful is that this might not have the rank equal to the rank of F. It really depends whether it's invariant or not. But just think about the region, and then in this case, it's very easy to figure out what the numbers are. Okay, I don't want to, I just wanted to justify why this number is crucial for us. All right, so now I can define singularities. And maybe I should say that I think this point of view is equal to Imperial, which is a very nice interpretation of singularity, from singularity foliation from an MMP point of view. So the definition is exactly very similar to what we're very familiar with. So we say that F delta is not canonical. So this is the definition. If, okay, so it's exactly the same form as usual. So if I write if y plus delta y, I'm sorry, for any birational morphism, proper birational, and I write this formula together. So the error will be of course supported on the exception classes, and it will be the discrepancy of the error will be supported on the exception class with coefficient equal to this. That's what we define by the discrepancy. Then what we want is that this number here is greater or equal than -1. For either, etc. And actually, maybe I should say canonical, sorry. And it's the same as the usual definition, where I just want this to be better. Okay, so again, my personal point of view, I mean, okay, I guess everyone would agree, is that the reason why we make a distinction between devices which are invariant enough is because we want, at the end of the day, we want to apply induction. And so we really don't want to have anything with positive coefficient it's invariant. Okay, all the invariant guys should be with coefficient equal to 2. I could talk about resolution song, but I'll rather go directly to the point of today. So the point of today is that is there a cone theorem and a base point theorem for this object? Well, since it's not known in general, I will call it a conjecture. So it's an attempt, sorry, to generalize whatever we know for the classic name of the problem. So the conjecture is exactly what we expect. So let's suppose that that is not identical. There is a bit more general version, which is follows numbers idea for non-local first, but I'm just going to focus on the standard one. So this is the very first part of the conjecture. There exist rational curves. Okay, and I don't stop here. Besides the fact that they're rational, what is going to be very important for us is that they are tangent to F. So tangent to F, of course, I'm going to say something more. But what the tangent to F means, they contain a leaf of F. Or in other words, the tangent vector and the generic point of the curve is basically containing this shift here. So it's really what you expect to be tangent. Okay, so let's say, okay. Okay, so first I need to tell you the theorem, the conjecture, so the theorem such that exactly what the cone theorem says. So the cone of curves can be split into parts. The part that is positive, which is the set of all the cycles for which the FSF is non-negative, plus all these extreme arrays generated by all these curves. Okay, so this is the first part of the conjecture. And as I say, really it's not only about rational curves, it's not only about the structure of the cone, but what is important is very much the fact, and will be very much crucial for us, it's going to be extra information, which is the fact that it's tangent to F. Okay, so the second part of the theorem, is the base point field theorem, which is exactly what you expect to be true. So if F delta is fundamental, maybe I should say F is still T in this case. And A is an element divisor. Such that L, which is equal to KF plus delta plus A, is an F. Then A is an F, then L is an F. Okay, so again, we need to be a little bit careful because many times we hear the fact that foliation is not such different figure. So the reason why we need to be careful is because, again, I'm taking delta to be in such a way that it does not contain any hypersurface which is invariant by the very definition of local number. Okay, so what is known about this conjecture? Actually, quite a lot is known. So first of all, the cone theorem, which is the first part of the conjecture, is known for any foliation rank 1. And this is due to Bogomolov equilibrium. So don't miss it. So, for the law of Macmillan, prove that in any dimension, so for any n, and for rank equal to 1, this is the cone theorem, sorry, only the cone theorem is okay. I don't know if with this cone theorem it's okay. At least I never seen it done. In full generality. On the other hand, in dimension 3, the first dimension 2, so I think this is a combination of work by Spicer and then 2 works with myself and Spicer. So Spicer proved the contour for canonical foliations, and then we proved it for rank 2, and on a threefold, and then we proved it for more general singularity context. So this is, well, I don't know the years, but what we prove is that for in dimension 3, or dimension less than 3, both are okay. So the base point fit theorem both rank 1 and rank 2 was proven by myself and Spicer. And also, so of course, why do we care about this? Is because we contract an extremal rate. So what we also proved is that, and if an extremal rate defines a flipping contraction. So what does it mean? So suppose that we have a foliation on a variable dimension 3, I suppose, and we have extreme array, one of these curves, which defines a morphism which is birational small, in other words, contracts a bunch of curves, then the flip exists. And then actually there was a work by Callum and Svaldi, which proved that 50 minutes. So in this case, at least in rank 2, and rank 1 it was proven by McKenna and also by Callum and myself. So in pretty much in the Mina model exists. MLP minutes. Okay, so it really works. I mean, in dimension 3, it seems that everything that we want to be true is true. So what I would like to do today instead, it's a different picture, which is related to algebraic integration. So, first of all, just to motivate, let me say that very briefly, by the theorem of Miyaka, and then component pound. I will be brief. So I'll just say that if that is canonical, then the foliation is semi-loop, even though the F is not set. So I will explain what semi-loop means. But the reason why I mentioned this result is because if we assume some negativity, we have a lot of rational curves which are tangent to F. So this is exactly what semi-loop means. So F is semi-loop. If for any point x in x, there exists a rational curve which is tangent to F. So it's based on, it's more than just I mean, just want to say the x is semi-loop. So I really say, even though the leaves would be not algebraic, it contains a lot of algebraic curves, which is very strong. So it's an extra reason why we're interested in algebraic integration, although it's not the main reason for today. Okay, so what is the idea of algebraic integration? Algebraic integration means that the general leaf is algebraic. But since we only care about the birational geometry of this object, I will give a stronger definition. I mean, I will give a slightly stronger assumption. Meaning, I will say that it's induced by a foliation, which is not a bit stronger than what I say, but it's the same if you allow taking rational numbers. So let me just say what the context is. Let's suppose that F is a morphic from X to Z, which is a foliation. So in other words, I'm assuming that the fibers are connected and is surjective. Then we can take the kernel of the tangent boundary, I mean, of the differential map. Exactly what we did when we talked about Frobenius theorem. But in this case, we do it globally. And of course, this might not be a subsheaf of X, which is saturated, which is such that the quotient distortion phase. So what we need to do is to take the saturation, which of course, the reason is because there could be multiple fibers. Whenever there is a multiple fiber, this guy here is not saturated in sectors. So, well, you can imagine this is closed by the brackets. So this defines a foliation F induced by little f. I mean, this is just a definition. I mean, foliation F induced by F, it just means that you're taking this subsheaf. Okay, so which are special cases of these foliations? So the special case, which would be easy to do calculation, is when this morphism from here, besides the integration, it's a two-dimensional. So let's assume that F is a two-dimensional. Then, I mean, we can do it in general, but the calculation becomes much easier. So by good dimension, I mean that all the fibers have the same dimension. Then the calculation gives us, so I should write this, and I should stop here if there was no saturation here. So in other words, if there are no multiple fibers. But we need to keep track of multiple fibers, and the error is given by this object here, where these are all the vertical divisors. So vertical divisor means that it does not dominate Z. And what else? And then this is the multiplicity. So where for any p divided by the surface of Z, we write f star of p would be the unit, the sum of the d with coefficient of. So it's really a multiplicity of the pullback of the pre-image of p along all the divisors. Okay, so basically what we want to do is to start the minimum problem for this object. So for instance, you can assume that there are no multiple fibers, and you can start the minimum problem of this guy. And this, as far as I know, has never been too much studied before. I mean, I don't really know much about this besides using foliations. It looks like foliations in natural context to work on the minimum problem for this guy here, with some error. But I don't know, I might be missing something. So the question is, are these theorems true? Sorry, are this conjecture true for this kind of foliations? And this we still don't know. But in some cases, the answer is yes. And those cases are good enough to have some application. So this is the content I'm going to work with. So this is due to Andrew, myself, Spicer, so let's suppose that we are in the context that we were just now. So let's suppose that we have a fibration from X to Z. And let's suppose that we have a divisor P on X. There is a reason why I don't put it delta, I will be clear in a few minutes. B on X, such that XB is a lot better. Okay, this is not very much as immediate, but let's keep it at this sort of forget it. Then we say that the pair XZ, by XZ are just it's a smaller variation of this morphism. B satisfies, so here it's a lack of better words. Probably this time. If the following hold. So we couldn't come out with a better name, so we just go to this side. So what I'm gonna write is not extremely natural to say it for the first time, but it turns out to be very good in application, and I will try to justify why. So I don't know, maybe there is a different way to look at these things, but for us, this is not to be the right point of view. So first of all, I'm assuming that there exists a device or reduced devices on that, such that the pair sigma z is not moved. So I'm assuming something very strong about that. Although probably it's not me, but I will explain why this is not a big deal. So the second property is that the vertical part of B coincides with the plane measure of the sigma z. And you need to be careful. I don't mean the pullback. I really mean the previous because I really want a coefficient one device, a reduced device. And the third part, which is probably the least natural one, is that for any z in z, close point, and for any p reduce effective divisor, such that the pair sigma z plus p is not smooth at z. So in other words, I have already something which is not moved, and I give my freedom, the freedom to add more to the boundary of sigma z in such a way that this property is preserved at least around z. Then, for all these cases, we want that the pair xb plus the pullback, and here I really want the pullback to be, is not canonical around the preimage of z. Okay, it's a bit of weird definition here, this one. But really, this is very similar, although I'm not going to go into details, to asking that the formation induces local anomaly. There is very much a correspondence between this guys here and local anomaly for the formulations. That's one thing. Then the good news is that we can always get something like this. And this is exactly what I'm going to talk about next. So we are always able to, given any figuration, to reduce to this picture if you're willing to work on a different type of model of the pairs. So let me state the theorem. The theorem is to do, of course, they write in a completely different way, but this is to do a random level. So let's suppose that we have any morphism, so any formation. And be any effective divisor, such that xb is a long term. Then there exists a diagram and there exists b prime on that with the following properties. On x prime with the following property. So the first property is that this pair here satisfies from this side. Okay, the second property is that, oh, sorry, should I say before, alpha and beta birational. This is, of course, an event. And the third property is that, so of course I need to say something between the relation of xp and x prime. So the third property is that
XB and X prime prime are frequent over the general point itself.
So you need this condition log pair only generically.
Yeah, always.
It's much weaker.
It's much weaker, yes. Frequent over the generic point. Yeah. I mean, we need much less than what is written here. By the way, property star implies log. This is obvious from this definition. All right. Any questions? Okay, let's see. Again, I promised to give some applications, so hopefully I will get there. But let me say the theorem before I give the application. So the theorem is exactly what, maybe let me say a few words without writing down. So what are good things about, okay, first of all, how do they prove this? For them, they don't care about property star, but they care about toroidal morphism. This is a toroidal morphism with respect to the pair X prime and prime. So that's one thing. The second good thing about property star is that it's preserved by MMP over Z. If you run an MMP over Z and your pair satisfy property star, then all the other steps of the MMP satisfy property star. So from this point of view, it's very good. And also, one thing we proved, but I'm not going to write it down, is that there is something called, something a bit stronger than this, is something called property star modification, which is the equivalent of a DLT modification, where we don't just extract random devices, but we extract devices, local samples. Okay, so I want to talk about the theorem, and the theorem is exactly that these two conjectures are true for the formation in this context. And then I will explain why we do it. So the theorem by the same people is that both the cone theorem and okay, I should just say the context first. Sorry. Okay, I'll write first. And this theorem. Theorem hold for foliations, for foliated pairs, for pairs F delta, where F is induced by morphism F from X to Z, and delta is the horizontal part of B. Remember, I don't want invariant stuff to be inside delta. And well, of course, I'm assuming that the pair X delta B satisfies property star. So I want to unpack that. Sorry about that. I should have said, let's suppose that X delta B satisfies property star. Let's suppose that F is the formation induced by the morphism, and delta is equal to the horizontal part of B. Then the cone theorem holds, the base-point theorem holds, and also if the extrema right is defined a flipping contraction, then the flip exists, and we want to product domains. All this is very natural. So everything holds. Actually, there's a work in progress with Callum, with Spicer, where we are trying to prove, and we're in the progress of proving that the same theorem should prove for any actual information. But okay, let's try to understand why we care about this theorem. So I don't have time to talk about the proof. The proof is really by induction. The singularity is a better behaved than random foliation. So we can restrict to some good upper surface and things work out well. So what I would like to talk about is some application. And this is very much following the Shapiro paradigm. And also, I would like to explain why what I'm going to talk about follows from the proof. I mean, I'm going to talk about something completely unrelated, at least in appearance. I'm going to talk about the canonical bundle formula in a Shapiro generalized way. And then I will explain how this theorem helps to prove what I'm going to say here. Okay, so let's suppose that we have So fortunately, many of the definition you probably seen before. So I'm going to assume that XB is a lot of comparability, like Professor would say it will be much less than this, but let me do this. So we can define, you probably seen before, without any assumption, the discriminant of this. So we define the discriminant to be, so the discriminant of this criteria to be a Q divisor on Z given by, it's the usual discriminant that you probably saw in the usual current format for positive definition. So 1 minus the sum of 1 minus 1 times B, where it's a divisor of that. And of course, I need to tell you what the gamma is. So sorry, I need to actually I think well, 2 minutes, please. Sorry, I will continue. Sorry about that. So I need to define what is gamma p. Gamma p is the number that defines the coefficient of this divisor. It's usually defined exactly like as always. It's a soup of the piece, a real number, such that the pair xp plus x star p is not canonical around the general point of p.
T.
Sorry?
T times F not.
Oh, thanks.
Yeah, T.
Yes. And of course, when I say general point of p, I mean the perimeter. Around the perimeter of the general point of p. Okay, so what is this guy? So first of all, for general p, at least equal to 0, it's obvious that gamma p is equal to 1 for the general divisor. So this is a function more than general. It's for almost all divisors. So this is very sum. So this is well-defined divisor of that. And also it's the natural generalization, I think this is to matter, it's the natural generalization of the Q divisor for electric population as defined by Kodala. So I don't have time to talk about this, but maybe many of you already saw this object here. So, and again, for the Shoguro, we define the moduli part of this. So the moduli part. So here we need to be a little bit careful because we're not assuming anything. We're not assuming LCT or anything like that. So if really it's on X, it doesn't need to go on that, if you know what I'm talking about. So it's defined as the X plus B minus the pullback of KZ plus B. Okay, here I'm cheating a bit. So this makes sense exactly, it's 2 factorial, or if F is a dimensional. If not, you need to make a little bit of an effort to define it. So most of the time it's defined. Otherwise, you need to reduce it.
Stabilized.
Stabilized, yes, exactly. So if it's not well defined like this, you just make exactly a diagram like the one I did before, this one, and you define the kind that Professor should was saying, then you match it to that. This is a good definition. Oh, to X, sorry. Okay, so again, this should look familiar. It's the moduli part. You should measure how far is F from this, how far is this pair here from the isophilia. Okay, so let me mention the theorem. And I'm trying to finish it time. So this is the same thing. So again, one more time, let's suppose that we have a pair like before. So let's suppose that F is a relation, and then XD it's a lot or whatever. It's enough to see what comes next. So what I'm going to ask, the only sentence we're going to make, otherwise there is no proof that what on the right is correct, is that the x must be exactly net. So you should think of this to be a generalization of the usual local canonical trigger formula, right? Because usually you assume that the x b is triggered with respect to every fiber of f. Here we're assuming just that it's net. Okay, then it's very similar to that there is the theorem just now. There exists a diagram, and there's a reason why I do it like this. So this is that, as usual, this is alpha, this is the n, and there exists beta. Okay, such that on experiment, of course. So such that the first line is the same as before. XP and X prime B prime are crampons over the jump point of Z. The second part is that we're not the medial right here, so I don't. This is proper. Birational. Exactly like before, this is not proper. This is a birational. There's no way that it's two otherwise. At least. And of course, again, the most important part. So it satisfies the property star. This is the easy part. It follows from a gram which value. But most importantly is that this moduli part is net. So with this object, I mean the corresponding moduli part of this pair here. I mean the pair defined by this solution. So this guy here is
Always.
yes.
It's not proper. It's not proper in regular sense, but the birational is proper.
Yeah, no, right.
Birational.
Yeah. I mean, it's not defined. It's not that's right. Okay, so I don't have much time, but let me explain in a few words how this theorem is proven and why and how it is to the full theorem. So first of all, we reduce text of Abramovich and Gallicaro to a variation which has property star. Now we lost F9. Sorry, I forgot something. Sorry. We assume the usual. Sorry. I will comment about this in 1 minute, but we run an MMP because after we run Abramovich and Gallicaro, we lost the assumption of BFNet. So we do need to run an MMP over Z prime. At this point, we got something property star. So the foliation associated will satisfy the cone theorem. And the cone theorem says that all the curves which are negative with respect to the BF plus delta are vertical. Yeah, they are tangent to F, more than vertical. So all the curves which are negative with respect to BF plus delta are generated by BCI, which are vertical. But we know that the fibers satisfy the property that this guy is not. So there is no such CI. So the magic word here is not rational. It's nice to know the rational, but it's in tangent. Tangent is the most important property. So all these curves will be vertical. But there are no such curves because we're assuming it's okay, sorry, I'll take 1 more minute to make a remark. The remark is that this implies the usual theorem for, so it's a new proof without assuming dimension flips. We're not assuming anything, it's really a proof by itself of the BNFness of the oscillating propagation. This is due to Ambro for, so after Ambro for gravity and Collar for local. So what is the advantage? The advantage is that we don't use any variation of structure. We don't use anything which is not a pure application of MMP and resolution singularities. So in other words, in many contexts, this is more generalizable than the usual one, because for instance, now this is a work in progress, but we do expect to do, for instance, positive version of this is to positive. So course, you need to be a little bit careful about singularities, but as long as the minimum the program puts, it should work in any context that you want it to work. So this is the advantage of getting something like this. Okay, thank you very much.
Any questions? Yes, speaker?
It's not that math. Well, the point is that this is right over the John fiber. So if you start with something not that math, you'll never be able to get something math. Because you should think that if you remove some varieties here, it's exactly the same pair. So whatever transformation you make, you're not going to get mathness. So yeah, any context, as long as this is not math, this is not going to be math. Never.
In certain sense, this is like the risky decomposition. So if you not suppose that, it should be
Yeah.
decomposition. And MX, it's
the
movable part of the risky decomposition.
Yeah, sorry, I should have said this is due to spice in the slide. Yeah. For the dimension field, yes. So for rank 2, what is your question? Oh, this is dimension field.
So for the algebraic foliations,
So if satisfied from this guy, yes, it was from, well, basically, no. Whenever the usual MLP works, then it will work here. So for instance, if you know that the foundation is relative dimension 3, then it will work. But if you don't know the classic termination, then it would work. For instance, you take exactly the point. You take exactly the point, it's exactly the usual.
So it's if it's a maximal rank foliation, it's just usual.
Exactly. If it's the maximum rank foliation, then it's the usual.
It's very strange. Maximal rank 1 is easy.
Exactly, yes.
Not between.
Exactly, yes. There is some kind of interpolation. Although even for, yeah, that's right. In some point of view, rank 1 is easy. Not always rank 1 is easy, but sometimes rank 1 is easy. Yeah, that's right. The contour is easy, but for instance, base point 50 is still this place. Hyperbolicity. No, this one I don't know anything. I mean, I don't know any consequence of the base. I know there are some words, but I mean, of course, everything we pretty much know about the grid if it's conjecture for foliation, but and McQuillan program is trying to use foliation rank 1 to try to prove like conjecture, but it's the MLP is part of this program, but don't have any application.
So the termination depends on the relative dimension or the
That's
dimension
correct.
of X.
So dimension filter.
I mean,
Relative
the,
dimension filter.
so all it depends on the general fiber, the dimension of the general fiber, or
And maybe worthwhile to mention about this almost precise condition. If we do not have star, in my case, there existed many examples when MX is not positive.
Oh, sure. No,
It's
that's
not stable.
fine,
Yes.
yeah.
So actually, it's almost like necessary condition.
Yeah. For this, we need this looks at the front of this level.
Any more questions? Yeah, then let's thank the speaker.
Could you?
Next topic is 11.